Hello again, physics students. So, I just realized that there were some things about the Van de Graaff generator that I wanted to include that I forgot to include in the last video. So I'm going to add a little bit more. So in the lesson that we saw before this video on the Van de Graaff, I mentioned that if you put something in a conductor that's surrounded completely, it shields that object from outside electrical effects, because the electric field inside of a conductor, even the cavity, is zero, unless you bring some charge in there with you. But if the charge is all around, then the electric field caused by that external charge is zero inside the cavity, even in dramatic cases like when there's a lightning bolt. And so I'm going to prove that to you. I'm going to take a sensitive little electronic piece of equipment, a calculator, and you see that it works. 2 plus 2, 4. Okay, so there's our test. Our calculator survived that. And what I'm going to do is I'm going to put it inside this part of the Van de Graaff, the discharge ball. Oops. The part that's going to get struck by lightning. Time to get it apart. Calculator. Inside, right? Oh, I'm not tricking you. I put it right in there. And now I'm going to put this cover on. Remember this piece. Tough. There we go. Let me connect it back to the sink. Make a nice ground. And by the way, I'm not doing it with this calculator because it's the school's calculator. If I had my own here, or if I had a cell phone, which I don't, I would put my cell phone in there. Even if I had an iPhone, whatever, for $1,000, I'd still put it in there. So, let's see what happens when we hit it with 360,000 volts. Okay, so lights out for a moment. Okay. So, took a few shots of lightning. Calculator, right? I'm not switching it out. Two plus 2. Let's do it again. There it is. It got struck by lightning, but it was surrounded by a metal cage. And it's counterintuitive because a lot of people would say, oh, lightning, let me get some rubber around me, the insulator. If I put a metal in the electrical socket, I get electrocuted. How does the metal protect me? We learned Faraday cage is what it's called. The electrons in the metal quickly move around and cancel the electric field inside the cavity. So another sort of application of this is lightning bolts in cars. People, you may have heard that it's safe to be in a car when there's a lightning strike. And a lot of people say, well, because of the rubber tires. They're insulating you so the lightning can't hit you and go into the ground, which is what it wants to do, hit somewhere else. The rubber tires are not the reason. Cars do get hit by lightning all the time, rubber tires. The rubber would have to be miles thick to stop a lightning bolt. In Van de Graaff Generator 1, I showed you the table where I showed you that rubber has a dielectric breakdown approximately 4 times that of air. So it's better insulator than air, but lightning can break through miles of air. A little bit of rubber, nothing, it'll go right through. And the most dramatic photo that I have of this is a really old, bad photo. I saw a lot of pictures online of cars getting struck by lightning, but none shows the effect as nicely as this one. Notice the lightning bolt coming down, hitting the car. The current in the lightning bolt goes through the metal, and here you could see it actually going through the rubber tire right there. All right, so poor quality photo, but it's the best shot I have of a car getting struck by lightning. Now, by the way, I've read that don't think that it's necessarily safe to be in a car because of a lightning strike, because you don't get electrocuted, but sometimes the car catches on fire. So you got another problem. Not so safe after all. All right, so one more thing I want to show you, not with the Van de Graaff generator. To me, it's even more amazing than the Van de Graaff generator. There's a video, okay, that I'm going to show you, but no, the computer went to sleep. Let's revive it. Okay, so have you ever wondered this? Oh, I'm out of focus. So when you work on wires, you might know in a house, if you want to work on a circuit, you go down to the panel, you turn this breaker off, and then you fix whatever you need in the circuit. And that's fine in your house because you could turn a bedroom off and just tell everybody, hey, you know, the lights won't work in the bedroom and it's fine. But think about this. The wires that come in and feed towns or even cities, what if they need to be worked on? Have you ever heard of an announcement? Maybe the governor comes on and says, all right, everybody in New York City, we got to shut the power down for 5 hours because we got to fix a cable feeding New York City. Never happens. The power runs for decades without interruption, and people still work on those lines all the time. Even more surprising, the wires that feed New York City, coming from some power plant, long distances, maybe 1,000 miles, maybe they come from Niagara Falls. Those wires are charged to 500,000 volts. Now I took 360,000 from the Van de Graaff and I survived. And why? Because the charge in the Van de Graaff was like 1/1,000,000th of a coulomb. So when I multiply 360,000 volts times 1/1,000,000th of a coulomb, and then you have to factor in that the voltage drops as it's discharging. But the point is, there's not much total energy because there's not much total charge. Yes, the electrons slam into my hand, but there aren't many of them, and I survive. But if you touch the 500,000 volt wire that's feeding New York City, the charge, the coulombs that's heading to New York City is enormous. And now you have both effects. Every single electron that tunnels through your body goes with tremendous energy. So that's the voltage. And then there's limitless electrons to go through the body. And what would happen is if you touch one of those lines, not like me, a little spark of Van de Graaff, your body would vaporize. It would literally explode like a bomb. There'd be nothing left of you. That much energy would go into you. So now, how do people maintain and work on those wires? Climb a ladder and grab it? No way. But yet they do. And they have to wear a suit, a special suit, to be able to do this. Now, if I asked you, what kind of suit do you think you need? Most people say, oh, rubber. You know what? 500,000 volts will jump through rubber, no problem. So what kind of suit would you wear? Well, the video is going to show us. An amazing video. First time I saw this, it blew me away. Okay, I couldn't believe it. So we're going to watch it once through without me saying anything. And then I'm going to rewind it, and then there's going to be some commentary to explain. So let me remove my little paper blocking the video. Old school. If I put this projector to sleep. It takes like 5 minutes to warm up. So do the old school cover with a piece of paper. Oh yes, I also have to plug in the audio here. So let's see.
I don't give two hoots and a holler about flying inside a helicopter. Put me outside. That's where I want to be. On a magic carpet. Back in the late 1800s, there was a gentleman by the name of Michael Faraday. He had a theory that if you enclosed a man in a metal cage and energized that cage at whatever voltage, the man would still live. The voltage would flow around him. I wear a hot suit. It's 75% Nomex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference from the electricity. As long as the helicopter is isolated from ground, we have the ability to bring ourselves to the same voltage potential as the line, like a bird on a wire. Our pilots are very smooth. It's like they can read our every thought. There's such a hunger for electricity these days. Nobody wants to take lines out of service just to maintain them. I've had many people ask me, do you think what you do is safe? And I say, well, in our operation, everything that we do, every move that we make is thought of and rehearsed before, so it's as safe as crossing the street. It's not a job for a hot dog. There's only 3 things I've ever been afraid of. Electricity, heights, and women. And I'm married too.
Okay, so there it is. What a remarkable video, crazy. So as I said, we're going to go through it now and understand the physics, and I'm going to highlight as best I can what he's saying, because I don't know how well the sound will work now, but let's see. Yeah, very soft. So he's coming because in a helicopter, because if he goes up on a ladder, as I said, and touches that, there will be 500,000 volts between the ground and the wire with his body in between. A goner. So the helicopter comes and brings him isolated from the ground. The only way to touch that wire and not get killed is with the helicopter. But even then, you saw the sparks when they got close. If he reached out, sitting on that helicopter to that wire, now there's a voltage difference between the helicopter and the wire. And what's going to go between? His arm. So there'd be a massive current going through his body, which would set his suit on fire. So he's got this wand connected to the helicopter, and so the lightning happens to the wand, not his hand. Now notice he's going to touch eventually it to the wire. And what he's doing is he's bringing the voltage of the helicopter and the wire to the same, and then he clipped this on, so he doesn't need the wand anymore, but the helicopter and the wire are connected. They're both 500,000 volts, no voltage difference. So when he's touching and the helicopter is, between the helicopter and the wire is his body, no voltage, no current through his suit, he doesn't get a shock. So now he's putting the equipment on, but again, that connection's maintained. Then once he climbs onto the wire, now he's got to let the helicopter go because they're hooked, right, with a cable. So he's going to take the wand again, because if he disconnects this and puts it in a bucket, the only thing between him, between the helicopter and the wire is his arm. So the wand again comes to serve so he could break the gap, not with his hand, but with the wand. And now they're isolated again. So there he is. And he said that his suit is a certain percentage stainless steel thread. He's wearing a metal suit to touch electrical wires. Crazy, blows your mind. And some flame retardant material also in this suit in case something bad happens. So there he is wearing a metal suit on a perfectly charged wire of 500,000 volts, okay? Isolated from the ground, and he's okay because he's in that Faraday cage, which protects him. The electric field in his suit is 0. Now, a helicopter comes, he needs the wand again to bring them to the same voltage so that, now he's going to clip, so that he could climb to the helicopter safely and not be the gap between the helicopter and the wire equilibrate with their voltage. Then he uses the wand to separate again, and there it is. So let me stop. Oops. All right, well, I guess, I should turn the light on first, otherwise the camera will get overwhelmed. Okay. Oops. All right. So I don't know about you, but that video was mind-blowing. I just love that video. I watch it every year. So fascinating stuff, a beautiful application, an important application, so we don't need to shut cities off, of these Faraday cages making the electric field inside of a metal shell 0. In this case, the metal shell was his clothing. All right, so I hope you enjoyed it as much as I did. Fascinating stuff. But I think I've covered everything that I wanted about the Van de Graaff. Who knows, maybe there'll be another segment when I think of something else. If so, then I'll see you then. Or if not, then I'll see you in the next physics video.